Astrophysics, the branch of science that seeks to understand the universe and the way it works, has long been interested in the mysterious concept of black holes. Black holes are regions in space with such immense gravitational pull that nothing, not even light, can escape from them. Their existence was first theorized through Einstein's theory of general relativity in the early 20th century, and over the years, extensive research and observations have reinforced their significance in our understanding of the cosmos. One of the tools researchers use to figure out the realities of space is the James Webb Space Telescope, and while it wasn't actually meant to study black holes, since the focus is on the entirety of observable space, it's bound to pick up information about black holes too. But the problem is, the information it's picked up is the exact opposite of what we were expecting. Greene has just confirmed the recent findings, and turns out, according to the James Webb Space Telescope, black holes aren't real. Join us as we bring you all the details.
Telescopic imagery from the Event Horizon Telescope of the black hole in M87, that ripple in the fabric of space was the most direct evidence
About this shocking discovery and how it's turned the world of science upside down. Black holes are cosmic entities predicted by Albert Einstein's theory of general relativity. According to this theory, massive objects deform the entire fabric of space-time, creating what we perceive as gravity. When a star runs out of its nuclear fuel and undergoes a supernova explosion, its core collapses under the sheer force of gravity. If the remaining mass exceeds a critical limit, known as the Chandrasekhar limit, the gravitational collapse becomes irreversible, leading to the formation of a black hole. The no-hair theorem suggests that any other distinguishing features of a black hole, beyond its mass, spin, and charge, are considered hair, and are believed to be lost beyond the event horizon. This event horizon acts as an impenetrable boundary, beyond which information is seemingly irretrievable from an external observer's perspective. So, to put it in one sentence, conventional black holes have been thought of as relatively simple and devoid of any further distinguishing properties. However, in a remarkable study, Sasha Heiko, Stephen Hawking, Malcolm Perry, and Andrew Strominger challenged this traditional view of black holes. Their groundbreaking research presents the existence of what they call soft hair in black holes, suggesting a more complex structure than anyone previously thought about. Soft hair refers to a collection of quantum properties that are thought to reside on the black hole's event horizon. Unlike conventional hair, soft hair is not associated with the black hole's mass, spin, or electric charge. Instead, it is believed to have subtle quantum properties that encode information about the black hole's interactions with its surrounding environment. The existence of soft hair would have profound implications for our understanding of black holes and the nature of information in the universe. It could potentially resolve long-standing questions related to the information paradox concerning what happens to the information of matter that falls into a black hole. The idea of soft hair hints at the possibility that black holes may retain subtle quantum fingerprints of their past interactions, raising the exciting prospect of retrieving information that was once thought lost beyond the event horizon. And if that's true, then what the James Webb Space Telescope found would be true too. But if you reel things back in time a little bit, this concept has actually been there for a really long time. Back in 1974, Stephen Hawking proposed a groundbreaking idea called Hawking radiation. According to this, black holes emit radiation over time, which causes them to lose mass and eventually disappear. At the time, though, this radiation seemed to be random and didn't carry any information about what fell into the black hole, which clashed with the principle of information preservation in quantum theory. Scientists did try to combine quantum theory with gravity to solve this paradox, but they ran into mathematical problems and couldn't make sense of it. The situation seemed quite confusing. This is probably why the theory didn't actually pick up and somewhat disappeared as the world of science went on. However, a recent study led by Netta Engelhardt and her team made exciting progress. They re-examined Hawking's formula and found a new calculation suggesting that information does escape black holes through their radiation after all. It opens up a new way of understanding how gravity may be intricately linked to the informational aspects of the universe, and if gravity isn't quite the same as we'd always thought it was, then the entire basis of what makes a black hole is what it is challenged too. But the problem here is that how could something so powerful be totally false? Is that even possible? Well, yes. Observing and studying black holes pose significant challenges due to their nature and the vast distances involved. Observational limitations have played a crucial role in shaping our understanding of black hole signatures, and at times, they may have led to misinterpretations. As we've discussed earlier on in the video, accretion disks are essential for understanding the behavior and properties of black holes. But in the past, telescopes faced significant challenges when attempting to study these accretion disks in detail. Their limitations in resolution and sensitivity hindered a direct view of the accretion process near black holes. The accretion disks around black holes are typically relatively small and distant, making them difficult to observe with the precision required to grasp their intricate features. To overcome these limitations, scientists resorted to indirect measurements and studied the X-ray emissions from the accretion disks. Since X-rays are highly energetic and able to penetrate obscuring dust and gas, they provide valuable information about the presence and characteristics of the accretion process. But the thing is, relying solely on X-ray observations had its drawbacks. The lack of direct observations meant that some aspects of the accretion process and the black hole's properties remained unclear. For example, the exact structure and dynamics of the accretion disks, as well as the distribution of matter within them, were not fully recognizable from indirect measurements. As a result, misconceptions or incomplete understandings about the nature of the accretion process and the black hole's behavior may have emerged, shedding light on the nature of accretion and other physical processes, which for the most part have just been theorized about this whole time. Although the JWST operates outside Earth's atmosphere, it is equipped with adaptive optics that correct for residual distortions. This technology further enhances the telescope's spatial resolution, enabling clearer and sharper images of black hole systems. But even if you take all of that out, there's one thing that really puts it above everything else, literally. The JWST's position in space allows for extended and uninterrupted observations, overcoming the challenge of long exposure times needed to study faint black hole emissions. Longer observation times enhance the signal-to-noise ratio, resulting in higher quality spectral data and more robust scientific findings. Because of that, it can observe black holes at various infrared wavelengths, providing a comprehensive view of their properties. Multi-wavelength observations enable researchers to study different aspects of black hole systems and gain a more complete understanding of their behavior or lack thereof. Plus, there's also the fact that the JWST is an international collaboration between NASA, ESA, and CSA, bringing together the expertise of scientists from around the world. This collaboration is great because there's an exchange of ideas and the pooling of resources, maximizing the telescope's potential for groundbreaking discoveries in black hole research. So even if one department has a bias or has confusion about a certain discovery, they have more than enough people at their disposal that just make sure that all of the data that makes it to the public is proven and reliable. With all of that, there's nothing better than the JWST to bring in information about black holes or to prove that they never actually existed in the first place. But which side of this argument do you land on? Let us know in the comments below. If you liked this video, please give it a thumbs up, and like always, we'll see you in the next one.